I will try to explain as clear as possible. So the title is Stability of Young-Mills vacuum state. And so how to move? Yes, okay, this way. So I will have a short introduction, and then I say about effective Lagrangians in QED and Young-Mills theory, because it's a generalization of the Heisenberg-Euler Lagrangian, which was discovered in 36 in Leipzig. And then I will formulate what is the problem with the vacuum stability. I discuss in details the polarization spectrum and the negative unstable mode, which produce this instability. And then I explain that a nonlinear interaction of negative unstable mode actually eliminate this problem. And then we will see that there is a actually imaginary term which was found in the one loop approximation is just an artifact of the approximation of the quadratic approximation, let's say. So, as you mentioned, this is a last publication which was devoted to this question of the stability of Young-Mills theory. This in 23 was published, and here you see this old publication which was in 77, including my PhD somehow. So, what is the problem? The problem of vacuum stability. So, the effective Lagrangian in Young-Mills theory has this beautiful simple form. As you see, it is a classical part. Here is this F. It is just a G mu square, classical action. And there is a quantum correction, which is beautifully was integrated and gives such a simple result, which is just F log F. And obviously, it's well-defined expression. And if you draw you can calculate the energy. And if you draw the energy density of the vacuum states, you will see that there is a condensate of the chromomagnetic fields, because we have here, as you see, this second invariant equal to 0, and this is positive, therefore it's chromomagnetic vacuum. And it is equal to lambda QCD in a renormalization scheme, which I will explain. Lambda is a dimensional transmutation parameter, but it depends what type of regularization you use. So it is just, I will explain what type of regularization it is. Now, you can calculate magnetic induction here, just differentiating Lagrangian over your chromomagnetic field, and you will find the vacuum suspectibility, and it is it's larger than 1, and it is paramagnetic. So, which means that Young-Mills vacuum is paramagnetic, which means that if you impose a chromomagnetic field, vacuum will amplify it. And this is an analog of the Pauli paramagnetism. The reason is that in QED spin is equal to electrons is equal to 1/2, but in QCD it's spin 1, and that's make a big difference between these two theories. So now what the problem is? If you calculate the spectrum of the vacuum excitations of the gluons, you will see that n is running from 0 to infinity. So if you take the lower state, n equal to 0, you see that this is a momentum longitudinal to the magnetic field, right? And this is the transversal part, which is quantized. Now you will see that the energy square is equal to k longitudinal minus gh, and for momenta less than gh, we have a negative mode. And this negative mode produces imaginary term, in an imaginary part contribution to the effective Lagrangian, which is written here. That was discovered by Nielsen and Olesen in just a year after publication year after my publications, which was 77. So therefore, this vacuum energy, as you see, has this shape, and this is a condensate. So if there is imaginary term, which means that the vacuum state is most probably is lower. That was a consequence of this fact. Okay. So now I will give a short. I was in Leipzig, actually. We were studying with in Yerevan. There was a group of students from Eastern Germany, and we become very close friends with Roland Kirchner, and we live in the dorm together. So I was visiting him frequently, and I was happy to see some photos in the Institute of Theoretical Physics where Heisenberg was working. And this is a photography of Hans Euler, but he died during the war. I mean, the Second War. Yes, so that's the effective Lagrangian of Heisenberg-Euler. As you see, it is some integral representation. It depends on two parameters, A and B. This is electric field and this is magnetic field. And when A is equal to 1, it just defines the critical fields. So you can see that this expression become very so at this intensity of electric fields, it's so strong that the pair will be created from the vacuum, and that's a Schwinger effect. But in reality, it was a Sauter in 31 who discovered that such a strong field will create the already pairs, electron-positron pairs from the vacuum. And then there is on this field, you have the critical field is about 10 to the 13 Gauss. It's very strong magnetic field. That's conclusion from here. Also, beautifully, you can expand this for weak field, and you will see that to the classical Lagrangian, which is E square minus H square, there is this quantum correction, which is fourth order of the two invariants, right? This is E square minus H square, and this E times H in square. And this term associated with the fact that you have this loop of electron-positron pairs, and therefore it produces scattering of the photons. In classical theory, photons are not interacting, but through this loop, they interact. And if you calculate the cross-section is very small, it's 10 to the minus 33 centimeters square. And so maybe 2 or 3 years ago, the Atlas experiment looking for the scattering of two atoms through these diagrams, they find two photon outcome. And here is the background, and measurement shows that it is 78 plus minus 13 plus minus 7, 10 to the minus 3 centimeters square. So confirming the result of the Heisenberg-Euler Lagrangian. Now, in these publications, I was using a renormalization scheme, which I was developed in 77, and I was able to, in the limit of massless electrons or fermions, exactly integrate the Heisenberg-Euler-Lagrangian. And you see that it has again this beautiful logarithmic behavior, but it is with plus. You see, e square over 24 pi square. This plus is null, what is called Landau pole. And this Landau pole is visible here at this place when the field started to fall and goes into the vacuum become actually unstable. And so that's also visible in terms when you see the effective Lagrangian. So now at this time when people was looking for the instanton polarization of the vacuum by instantons, I was doing in parallel with Hooft actually, who was doing in 76. And we was doing with my collaborators in 76, but we use this polarization of vacuum with covariantly constant fields. We were thinking that to make it also to extend our calculations for instantons, but just an article of Hooft comes out, and it was a very similar calculation using background gauges. Very important to calculate effective Lagrangian in Yang-Mills theory. So there was also some publications in 65, but not understanding the result, and so in any case, and then this is articles which follow the publication of this effective Lagrangian. So here I summarize, simply summarize the Lagrangian. So in quantum chromodynamics, as you see for SUN theory, effective Lagrangian, you see the expression is very complicated, but it is a mystery that it was using this field theory regularization I was able to integrate this exactly, and you got this result which I already showed you before. So as you see in Yang-Mills theory, it is minus 11n96 pi squared g squared. That's a beta function somehow because here is a minus, and this is for fermions. If you have NF is number of flowers, so you see that it is this contribution is with plus. So logarithm in QED is with plus, and in QCD is with minus, and in energy it's just plus plus. So plus plus. Therefore, you have this form. Another is a result which can, if you have effective Lagrangian, you can calculate effective energy momentum tensor. So you can see that energy momentum tensor, it's a standard classical expression and has this quantum correction. But there is also a term which is proportional to g mu nu, which is conformal anomaly. If you take the trace now, g mu nu, this will give 0, but from here will be 4 times bg squared 96. So it was also was found in 77. Unfortunately, it was only in my PhD, but not in the articles, unfortunately, but in any case. So our aim to prove that there is no imaginary terms in the effective Lagrangian. So I want to show that actually this term is not there. I mean, somehow that's a result of the quadratic approximation. Okay, so how we will do that? One can do it in different ways, but most appealing and easy to understand is when you use Euclidean path integral representation. So this expression on the left-hand side from here is just physical things. You know, it's Hamiltonian of this quantum mechanical Hamiltonian. T is just a parameter And as you see, here we have energy states and eigenfunctions. But on the right is absolutely unphysical Euclidean path integral. So if you calculate this path integral, you will learn about energy states and eigenstates. So the same true in quantum field theory when you formulate it in this way, right? And it gives you effective Lagrangian. So in Young-Mills theory, the Hamiltonian is defined as chromoelectric field square plus chromomagnetic fields, where operators are defined this way. So we have a Euclidean action, which is written here with a field strength tensor. What we are doing, we are interested on by polarization of the vacuum, which is a solution of the sourceless Young-Mills equation. So we consider it B field to be a solution of Young-Mills equation when there is no source, external sources. So I like to take about this B field as vacuum fields because they are a solution of sourceless Young-Mills equations. So if we find some solution, then we are interested to see what happens with the quantum fluctuations around and how they to learn is this field stable or unstable, or what are the influence of quantum fluctuations on this vacuum field. So you substitute this expression, which is the solution of the classical Young-Mills equation, and you substitute into the field strength tensor, and then you take a square. What you will see that there is a first term, which is just classical action of your B field. Then there is a term, if you do the partial differentiation, this nabla will go to the left, will hit the G mu, and this term is 0. So the term linear in quantum fluctuations is 0. It's almost obvious. And then there is these nonlinear terms. As you see, there is if you take the square, there will be some quadratic terms coming from here. Here is another quadratic term, and there will be cubic terms, multiplication of this, and the quartic terms when this is in square. Okay, so I prefer to write how to say, to divide this the action, the Euclidean action, into the pieces. So this is a quadratic. So this part is not interesting. It just goes outside of the path integral. This term will go outside, and we are no anymore. We'll talk about it. But this term is 0, so the whole things which remain in the exponent, and we have to integrate path integral over the quantum field A, it is this term. And this term contains two terms. So one is quadratic. As you see, this is a quadratic in quantum fluctuations. And this term is cubic. You see it is A, and the nabla of A. This nabla is in the background field, so it is depends on B. And then there is this term which is quartic. So the solutions which we are looking for is just covariantly constant field. This is F mu nu, X nu, and it is in some color direction. And one can always choose that F1, 2 is magnetic field and 3, 0 is electric, but they are Euclidean electric field. Okay, so to somehow to take the path integral, we need to know the spectrum of the quantum fields in this B field. So equation is here. As you see, it's linear in A because we make a variation, and then we need to calculate the eigenvalues lambda. We use the background field method, this nabla mu by A mu equal to 0. It's a background gauge fixing condition, very convenient, and therefore the equation reduced to this one. So as you see, there is two terms. One is this differential operator of the second order, this one, and this is just a spin orbital interaction. So before we solve the full equations, it is very convenient to find the spectrum of this operator and then to find the full spectrum. So now this H0 is the term which we have here, right? Nabla mu, nabla mu. Now if we open it, as you see, it is a B field here in square. We open it and we get two terms. One term is, as you see, contain the H field, and the second term is contain the electric field. Because we are in Euclidean space, they are both oscillators. It's an oscillator in background magnetic field. I mean, it's just in quantum mechanics. It was classical things to solve. So, but want to do it in a nice way. So, how to do it? You have to introduce this operator C, C plus, D, and D plus. So C operators contain, you see, H, and the D operators contain E, electric field. And then the H, which we have here, this expression, become looks very nice. As you see, it's some operator. Somehow, remember when you write the oscillator in terms of creation and annihilation operator, is A crest A dagger A. So this is similar, you see. This is operator, let's say, and then this is its dagger. And there's D and a D dagger. And there is also remain these two terms, GH, GE. Now, because it's just as a standard oscillator, you can easily find that the wave functions are creation operators acting on the vacuum state, lower state, psi 0, 0. Psi 0, 0 is just Gaussian wave functions with H in the plane 1, 2, and with E in the plane 0, 3. So we have two oscillators in two planes, in 1, 2, and 3, and 0, 0, 3. And if we act on this wave function, you see that they have beautiful form. So it is polynomial, this polynomial in n, polynomial in m, and there is this h to the n and e to the m multiplied by this. Now, as far as we knew h mu nu, it is also easy to find that eigenstates, eigenvalues are 2n plus 1 times gh and 2m plus 1 times ge. So this, we have two oscillators, magnetic oscillators, so-called Landau levels, one can call it. Okay, so the important thing here is that these states have huge degeneracy. Now, how to understand the degeneracy? Degeneracy can be understood in the following way. If one construct, so we have psi nm, if one act on these two operators, d3 minus I times d0 and c1 minus c2 dagger, on the psi nm, we will get wave function which I define, you see, psi nm, and there's two indices, n0, m0. So this wave function has the same eigenvalues as psi nm. So you see huge amount, infinite amount of wave functions when n0, run from 0 to infinity, means that these energy levels are infinitely degenerated. So it is important to calculate the degeneracy. So how you can do it? Let's see, because the charged particles are rotating around the magnetic field, one can calculate the size of the orbit. So r square is the average of x1 square plus x2 square. I am looking just in the plane 1, 2. We have to integrate x1, x2 square with the wave function, and you will see that it is this size of the orbit is proportional to n to the quantum number divided by the magnetic field. Right now we can ask how many states n are in the radius less than r squared. So we can resolve this equation and find n0 plus 1. From this inequality, it will be less than gh r squared. We will multiply by pi, and we get gh times area in the plane 1, 2. Now, this was done by just for oscillator 1, 2, but if we go to 0, 3, this is m0, then it becomes proportional to the area in the plane 0, 3. Now, which means that if we want the total degeneracy, it's a product of these things. It is n0 plus 1 multiplied by m0 plus 1, and that will give us, as you see, gh over 2 pi, ga over 2 pi, and then because of the product of plane area in plane 1, 2, and 0, 3, that is equal to the volume, three-dimensional volume multiplied by t. It's not time, but just a four-dimensional volume. Okay, that formula is very important because it tells that all these energy levels have degeneracy, and we know how much it is. Okay, so we was working until now with this operator, which is nabla square, and we need to find now eigenstates of the full operator, which is h mu nu. It's contained this f mu nu. Now, it is easy, if you write the f1, 2, and so on, it's elementary algebra. You will find the diagonal fields, eigenvectors, right? It's b. I don't like to write b plus, just b and b minus, h and h minus. And then you will see that in addition to this eigenvalues, you see, which we already knew, this 2n plus 1 gh plus 2m plus 1 ge, this part of the spectrum comes from the first operator, which we already just find out right here. But this spin orbital interaction, because spin is equal to 2 to the 1 in the case of Young-Mills, you see there is a 2gh plus minus 2gh plus 2ge and minus 2ge. And these minuses is exactly which produce the unstable mode. So here unstable mode are coming out in the lambda 2 and lambda 4. So how you see, you should take the n and m equal to 0, right? If we take it n and m equal to 0, so remain the ground state of the oscillator, this gh and ge. And so here we don't have problem because it's plus gh plus 2gh, it will be 3gh plus, so it's positive. Now here, as you see, if we put n and m equal to 0, there will be gh, and there is minus 2gh, so remain I think that I did here wrong, right? So if we have 0, it will be GH minus 2GH. So it will be here, I'm sorry, here should be just GH, GE minus GH. And in the lambda 4 will be, again, if we put n and m equal to 0, we will get here GH coming from here, and GE minus G, it will be again GH minus GH. So there is no 2 here and no 2 here. So what you see here is that if E is not equal to H, then we have a negative mode in lambda 2 and lambda 4. So Leutwiller, in this publications, which was published in 80 and 81, he just stated that if we have a self-dual field, you see, if you have E equal to H, that's a self-dual field, right? Then this quadratic form is equal to H squared. And in that case, if E equal to H, because I'm sorry for this 2, then this term nullifies, is equal to 0, and we have 0 mode. And here we have also another 0 mode. So we will have, when n and m are equal to 0, we have lambda 2 and lambda 4 are equal to 0. And because of this degeneracy, which are discussed, it means that we have infinite many 0 modes. Actually, to work with 0 modes is very complicated. If you remember the work of Tchov, where he was calculated quantum corrections to the instanton, there is a 0 modes associated with the size of the instanton, with the position of the instanton. So it is four coordinates, x0, x, right? You can shift back and forth in 4 dimensions. Also, you have a rho, the size, and also you have a rotation, a full rotation of the instanton. But it means that in the action, eigenvalues are 0, and the functional integral is neutral. There is nothing in the exponent remain. So one should take special care about 0 mode. And here, it's not just in case of instanton, number of 0 modes were 4 plus 1 plus 3, it was 8. Here it's just infinite. And Leutwiller was unable to calculate contribution of 0 modes. So I was trying to do in 80s, in 70s, try to solve this problem, but I did not find a way how to do it. But this just a few years ago, I realized how it can be done. So what we will do, we will, like at Hof, we will introduce, you see this expression? This is nothing else but wave function, the degeneracy, you know, this n0, m0 are the wave functions which produce the degenerate state to the ground state, psi 0, 0. All these states have the vacuum energy, ground state energy of oscillator. So we take the superposition of all these wave function with this coordinate psi n0, m0. This is a collective coordinate, as Hoft was calling. So it's an amplitude of 0 modes. So therefore, our fields are superposition of all these 0 modes. So zero modes are in the plane 1, 2, and in plane 3, 0. So we have two complex numbers here, two complex numbers, but infinite of them. And here's another two complex numbers, also infinite of them, because it's summation over n 0. So we have to calculate the contribution of this zero modes. Okay, how to do it? Now, because they are zero modes, this quadratic operator is equal to 0, and in the exponent we have just 0, so it is just 1. Remain nonlinear term, which is written here, it has a cubic term and quartic term. So the first mystery is that if you substitute these modes into this expression, you will see that cubic terms equal to 0. Because of the colors, you know, some of their equal colors, and this, because it's antisymmetric over AB, this term nullifies. Okay, so remain only quartic term. Okay, so we, in the exponent, in the path integral, remain only this term in the exponent. And these are the fields here. Fields here are here. If we substitute these amplitudes of the zero mode into this quartic term, we will get something which depends on psi and eta, and we have to integrate over psi and eta. So before we do that, let's do first the positive mode. So what I write here, contribution of positive stable mode. So we have to sum, okay, you know, one loop contribution is equal actually to logarithm of determinant of h mu nu, and minus this logarithm, this is the contribution of the Gauss, Fadeev-Popov-Gauss. That's the one loop contribution. So because we knew the specter of h, so we have to sum over n and m, and also take into account that these states have degeneracy, right? And if we substitute it here, the logarithm can be parameterized with Schwinger-Fock parameters, ds over s, and here is the sum of eigenvalues. It is a beautiful exercise. As you see, I substitute these eigenvalues. You see there is n plus m plus 2. Obvious reason, because now we take e equal to h, so here h is equal to e, therefore it is 2n plus 2m plus 2 and so on, so easy. And so here is the eigenvalues, which are non-zero, they are positive stable eigenvalues. So we there's this exponent, we sum it, one can do it with some efforts, and you will see that it is become the integral. Yes, also you see degeneracy when this is all very important things, you know. So if h is equal e, here will be g square h square, right, times volume. And that's what it is, this term. You see g square h square is the term which comes from degeneracy. And these summations produce this, this beautiful sine square, sine hyperbolical square GHS, g square h square. So these expressions is very important to analyze. You see, this integral ds over s is beautiful because at small s, it defined ultraviolet divergency. And in s equal to infinity, at infinity, it's infrared. So to calculate effective Lagrangian, one should find a way to regularize this integral in both limits, in ultraviolet and infrared. That was that's what I told that it was I find it at 77. So the regularization is the following. You require that derivative of the effective Lagrangian over the classical Lagrangian at renormalization point should be equal to 1. So if you write the counter term here, the counter terms are they are proportional to the classical action. You write here plus z times f, and then you substitute it here and so on. And what you got, you see this term, which we just have recently here, this term. Now, as you see, this is a counter term, which is proportional to h squared. And this also h squared. But beautifully, you see, it's a sine square mu square s, and here is cosine mu square s divided by sine cube mu s. So we have a counter term, which we can take it h squared outside. So you understand that it is indeed the counter term. But because of this beautiful regularization, you can see that this integral now is converging at 0 and at infinity. So which means that this regularization allows you to regularize the effective Lagrangian in both regions, in ultraviolet and in infrared. Another amazing thing is that if you use a dimensional regularization by 't Hooft, there will be not ds over s, but will be ds over s to the power n over 2 minus 1. So each of these integral can be calculated in higher dimension, and then substitute and then subtract. And amazingly, you got this beautiful expression. So you see this h squared logarithm h squared. But this is just contribution of positive mode, right? So we now should take care of contribution of zero mode. So the functional integral over zero modes is dA, and this functional integral becomes the integral over the collective coordinates. In 't Hooft case, it was a d rho. If you remember, that was d rho divided by, there is some prefactor. But here we have to integrate over infinite of them, plus including the degeneracy. I just remind this integral. So first, I was thinking how to calculate this. And I just say, okay, let me do something else. So something else was the following. I artificially added terms alpha times GH and alpha times GE to the spectrum. If you remember, unstable mode was lambda 2 and lambda 4. And I added these terms. And obviously, if I just artificially added them, then and if alpha is let's say 3 or 4, there is no any more unstable mode. So lambda 2 and lambda 4 at n and m equal to 0, it gives you this type of contribution of zero mode. But then we have to add, right? So we have positive mode and zero mode. So this was a contribution of positive mode, and this is contribution of zero modes, which I write it here. You see, there is alpha here. And you will suppose, you can say, okay, but your result will depends on alpha, right? So what is amazing is that, again, you use this renormalization procedure. So this term we already discussed, that this was a positive modes. There's this counter terms, and then this is the zero mode as a function of alpha, as you see, and then this is the counter terms, which depends on alpha. Amazingly, if you calculate this integral, they are not this integral does not depend on alpha, and you recover this term is the positive contribution of positive mode, and this is contribution of zero mode. So if we sum this expression, we got this expression which we have before. So amazingly, this again sum up into the A11 g square a square to the 4 pi square, as it was before, without any imaginary term. But you can criticize, you say, look, this is artificial. You add this alpha, okay, it does not depend on alpha, therefore it's not very much convenient. Okay, so that's true. Let's do it everything correctly. So again, consider this nonlinear terms. Now, this cubic terms, as I explained, is equal to 0. And we have now the path integral over 0 modes, which contain just this nonlinear term. I just, if you put it here, epsilon a, b, c, and square, you get these two terms. One is, as you see, a mu, a square, but here a nu times a nu. So this is a quartic term, and we have to integrate over all 0 modes. So just for transparency, I take the first 0 mode with n and m equal to 0, which are written here. The amplitude you see is psi prime. Yeah, so psi prime is a real part, psi 2 prime is imaginary term. And here again, eta and eta 2 prime. Now, if we substitute this wave function into the exponent, we have to calculate the quartic term. So what we find is, you see these amplitudes of 0 modes, psi prime square, real part, imaginary term, real part, imaginary term, times the integral, 4-dimensional integral of the ground wave function. So that's integral. Now we have contribution to the path integral of 0 modes is, as you see, quartic in amplitudes times this integral. This integral can be calculated, and it is proportional to gh squared, and this is again quartic. So why before this integral, why the people was just stop? The reason is that, to integrate something which has a quartic interaction is almost a dead sentence. I mean, it is impossible to integrate it. But you can see what type of trick can be done here. I will introduce new variables, xi eta, which are divided by g times h in power 1/2. If we substitute here, this integral, you can see that the field dependence factorizes, goes outside of the exponent. Yes, and so remain this integral of quartic, and then the integration of the amplitude. So as you see, the full dependence on the field just factorizes from the path in the path integral. But of course, we have to take also the degeneracy. Now, this was just the first degenerate state. Now, if we take n0, m0, all of them, calculation is a little bit more evolved. So we have these gamma functions, amplitudes psi n0 m0 in square, you see, eta n0 square, and everything in square, as it is here. You can see if we substitute here n and m0, 0, we will get 32, because this expression is equal to just 1. Okay, again, one can make the same substitution, and dependence on the field factorizes to the in front of the integral. Okay, so we take this factorization. We should also take as many times as degeneracy is, which means that this expression should be taken in the power of degeneracy. Degeneracy is equal to g square h square, right? And this expression elevated to the exponent become the logarithm. So therefore we can read from here the effective Lagrangian, which is g square h square over 4p square logarithm g square h square to mu to the 4. So what we see that this expression is coincide with one which we obtained before with this artificial or whatever regularization. So it is g square h square over 5 pi square. And you see that the result is the same. Therefore, now we our effective Lagrangian is h square plus the positive mode and negative modes. So the Lagrangian remain again the same, and there's no imaginary terms here. So now, how much time remains?
Yeah, so we are almost at the full hour. So if you can kind of wrap up.
I have another 2-3 minutes.
Okay, that's perfect. Yes.
Yes. Okay. So the question is that what happens if I will disturb the self-duality conditions. So self-duality condition was that h is equal to E, right? So I will take it now gamma times h, which means that gamma is, when gamma is equal to 1, that will be self-dual point. But if gamma is less than 1, then we are not anymore in self-dual fields. When you destroy the self-duality, then negative modes appear. So these negative modes appear when n is equal to 0 and m is 1 minus gamma divided by 2 gamma. So because gamma is small number, you see m become large and large. So for small gamma, there is more and more negative modes, unstable mode in the system. So now we have to repeat our calculations, but now you see the expression, we have a positive contribution of positive mode, and of course it depends on gamma, as you see here, the gamma, and if we put gamma equal to 1, this expression, you see, reduce sine square gh square, yes, like as it was before. But now it is, you know, it's more sophisticated terms depending on gamma. Now, what happens with the negative mode? So this quadratic term is now has a negative mode. So if we leave this negative mode, of course it will produce imaginary term, but we have the quartic term here, additional. So therefore, one should substitute all these modes which I did not show you. We have to again introduce the collective coordinates, substitute into this functional integral. You will see that here there will be negative modes here, but there will be dominating term which comes from quartic interaction. And then the question is how you will be able to take the path integral with this nonlinear terms. And the trick is again the same. The beauty is that as you see, this substitution really extracts the whole field dependence, factorizes into the field dependence. It remains some integral which we don't care, just some number, n00. I define it here, or n0, m0. So therefore, again, producing the integration, we get this contribution from the negative mode, which has no imaginary term because of this positive term, pi to the 4. And the expression again coincides with the one which we have before. So the conclusion is that if we just include the nonlinear interaction of either zero modes or negative modes, because of the nonlinear interaction, instability, it becomes just an artifact of the quadratic approximation. So therefore, I would like to thank you for to participate in this talk.
Thank you for the very clear seminar. Thank you very much. I certainly sort of clearly enjoyed what you were telling us. I have questions, but I'll wait, since I'm the chair, to see whether there are some other people who also have questions. So if you have a question, please go ahead, unmute yourself and ask the question.
So it's technical, you know, it's a lot of details of calculation. So
No, that's fine. That's precisely why we would like you to, why we wanted you to sort of give the seminar, because we want to learn stuff. So okay, you are not quick enough, so I will ask my first question. So the first question I have is that you do have this temperature T that sort of is in some of your formulas, but I think what you're really sort of doing is you have like an infinite sort of system in the temporal direction. So T really sort of is no, T is not the temperature. T is like the size of your temporal direction or something like this. So, right, you have this V3
Can I interpret this as a T?
Yeah, this is beta, right? 1 over temperature.
Beta volume term.
Yeah.
Yeah, what is how as Coleman explained, this T H times T, right?
Yes. It's the inverse temperature. The length of the thermal circle.
Yes, okay, maybe. Yeah, I have to think about that. It can be so what Coleman says, and I will repeat, that when T goes to very large, the dominant contribution to this sum comes from the ground state. So
yes.
Which means that T goes to, oh, just a moment, let me see. T goes to infinity. It's the beta 1 over T. T
yes.
goes to 0. Okay, so when we have a 0 temperature, that's the main contribution is ground state.
Yes.
That's okay. Yes, yes.
But now comes my question, because as you know, in finite temperature field theory, so if your T parameter was not actually infinity but finite, you have to ensure that there are periodic boundary conditions. Does your background field B fulfill periodic boundary conditions when T is not infinite?
Boundary conditions are here, we take A and A prime, and then I take A equal to A prime. That's correct. So I should open the so you see here is the boundary conditions, which integral over Euclidean fields with the proper boundary values. So at 0 and at t are these two values, because the integral is coming from a to a prime. So that may be why you so at the end of the day, I think that, let me see, nevertheless.
So in your equation 2.7, you have this capital B, right?
Yes.
And somewhere later down, you sort of write that B is equal to x mu times something.
Yes, this is a yes.
This one, yeah, equation 2.14. Does that fulfill periodic boundary conditions?
No, I think that I did not take the periodic boundary condition, because if I took periodic, you are right, because if I put I cannot do the periodic boundary condition with this field. So therefore, I will say that it's, I have this A and A prime. So periodic boundary conditions to make for a constant field, yes, I think that Jan Amborn with collaborators, when they put the system on a lattice, they consider this field periodically, which means that when x, just a moment, when this x nu hit the boundary, you should ask the field to be equal to so which means that the flux is started to quantize. So that's maybe a good answer to your question. So if you consider this at t should be equal to at 0, this means that in exponent it should be equal to 2pn, which means that your field started to quantize. Yes, but I did not consider t finite. We send t into infinity, so it's an infinite volume.
Yeah. Now, if you send t to infinity, then you don't have this problem, because there's no finite sort of.
Yes. So it is interesting, to consider these things at finite temperature is also interesting, because if you consider these vacuum fields for cosmological application, I did this. Because I have this. So because we have from the effective Lagrange, we can calculate the T mu nu, the energy momentum tensor. Therefore, we can solve now gravity equations, gravity equations with this contribution which comes from the vacuum polarization.
Yes, very good.
That was another things, but Yes. So my understanding is that indeed, if embed periodic boundary conditions, then there is a quantization. Yes, my collaborators who is now doing on the lattice SUN, exactly that what happens. We have to, unfortunately, to quantize the field, because at the boundary, the field should be equal to the at zero, at the t and at zero, and that's you know, f h times l should be equal to 2pn, so it quantizes the flux.
Okay. Any other questions? I don't want to be the only one who asks. I have lots of questions, but I'll.
Yes, go ahead, go ahead. I will be happy.
I want to give the other people a chance. So if you want your chance, now is a good time to unmute yourself and ask a question.
I have a question.
Go ahead.
Yeah, for your Lagrangian, the term containing the 2f mu nu, you said that was the spin orbit coupling term. Can you explain
Yes, so
that notation?
yes, this term.
Yeah, exactly. Yeah.
So spin orbital interaction, it is just a moment. What is written here is the interaction of the spin in the background field. So it is h times s, this term. So maybe the orbital interaction is from here coming, and this is interaction of the external field or vacuum field with the spins of the gluons. So
I see. So
that will be more correct. So in quantum electrodynamics, it will be f mu nu times sigma mu nu. F mu nu times sigma mu nu. So it will be interaction of the background field with the electron spin.
Yeah.
That's why it produced this term 2gh, because yes.
Yeah, and the plus minus just comes from the structure.
Because of the orientation of the spin, yes. So I incorrectly was saying that it is spin orbital. It is a interaction of spin with the background field. So just power
spin of the background field. Yeah. Okay.
Yes.
Yeah.
So, but spin orbital is this term. This is the first term.
I see.
Other questions?
Thank you.
You're welcome. Yes. So sorry for misspelling.
No worries.
Okay, I have a question precisely on this point, the 228. So this is your sort of operator, and then you sort of, in 229, you basically sort of do these decompositions of your fluctuation field, A mu, by components, right? It's very explicit, A1 plus I, A2, and so on. And I think this is for SU2 probably. So I got very confused when I tried to, I tried to sort of do what you did in your spirit, but I tried to do it fully covariantly with like an A mu. I tried to sort of figure out what, if I wanted to write 229 in terms of just A mu and projectors, what these things correspond to, and I got lost. Is there a sort of simple way to write 229 just as projectors on your little A mu for arbitrary SUN?
So you have to diagonalize, right? So these are eigen states. So when you calculate the spectrum, it seems to me it is a very, very convenient. I try to not to write pluses, minuses, but I think that yes, of course you can. It is some rotation, right? So if you write this rotation in with some projectors, most probably it is possible. But why you want to do it covariantly? Because the spectrum is, of course, covariant.
Yes, I wanted to do it covariantly because you start out in the path integral formalism where you do your non-zero modes, and then you sort of do the zero modes in the operator formalism. But I got confused, so I would like to do everything in the path integral formalism without ever having to talk about operators.
Paul, but you see you see the summation and all these things for positive mode and for positive modes and zero modes are different. You know, first of all, when you do the stable mode, positive mode, the quadratic approximation is just, you know, converging. Everything is okay. There's no any problem. But when it is a zero mode, you have just, you know, quadratic part is here just one. So there's no any dumping. You know, you have to do something more than the quadratic. So, but I think that if you, so it is, you know, it is there is some lucky things happens. You see, what is the lucky thing? Lucky things, of course, I don't know if you clearly realize that this cubic term is equal to 0. If you do with other modes, it will be not 0. And then I don't know if so there's two mysteries here. First, cubic term is 0. Second mystery is that path integral is non-tractable. I mean, if you write this path integral and you say, I will calculate it, they will say you should be crazy. It is impossible. But what
It is not impossible.
Yeah, it is. I mean, look, there is you know, literature with quantum mechanics of x to the 4, right? Gx4, and nothing comes out.
It does. It does. It's a trick. I'm perfectly happy with the path integral 5.47.
But you cannot calculate it exactly. Yeah, you
yes.
need to calculate it exactly, and
yes.
to calculate this integral exactly is, I mean,
yes.
if you say someone, nobody will believe you. But
it's
look
possible.
what happens here. You see,
that's a different story.
Step by step, you got here. Look, this integral is psi to the 4, this powers of 4, and then look, this integration is outside of the, so this is exponent, right? Now make a change of the variable. If you do it c, g to the h to the 1/2, because it's a 4 power here, will be this term will be 1 over h squared. So h squared disappears from the exponent, but then you have here d psi, d eta, d eta, and that's produced gh in the square in front of the integral. So which means that all dependence on the field get out of the path integral. So what remains is some number, which I write is n00, multiplied by something which is 1 over h squared. Now, but this was just the first mode, but there's many of them. I mean, with m0, m0. So, and again, you know, you do the same substitution. You see here 1 over h squared, right? But then the result is very easy, you know, 1 over h squared in the power of h squared. Degeneracy is h squared, 1 over h squared. So this explains everything, you know, you have h squared in the power of h squared. So it is h squared logarithm h squared. That's what you want to receive, right? So this is things. So I remember some referees say, oh, maybe you can just calculate everything exactly. But you see, the full integral, maybe it is, maybe this expression is completely, you know, exact. Just logarithm, h square logarithm. I think that in some this n equal 4 or n equal 2 supersymmetric Young-Mills looks like this logarithmic result is exact, like Weber Seiberg-Witten result.
What theory is that? So n equals 4
4
is
supersymmetric Young-Mills.
but n is 4 super Young-Mills is conformal. There cannot be any logarithms, no?
N equal 2? N equal 2.
Well, n is 2. Okay, I see.
N equal 2.
Okay.
No, not 4. No,
Yeah.
no, 4.
Yeah.
Equal 2. I'm sorry. I just N equal 2. So it's called prepotential, whatever it's called. Yes. But no, I don't think that it is. It is. You can do it. This machinery through the old modes. So it is. Let me also show you, maybe in the if articles. Is it article? Oh, this is article. Yes. Yes, so I also did it for, in case of how Copenhagen collaborators do. You know, they introduce the amplitudes of the unstable mode. So this is A1, A2, you see here. And they are written in terms of this phi k. So they write the Lagrangian, which is written here, you see, negative mode. You see, this is a plus phi k square, which is a unstable mode. Quadratic part is unstable, right? It has a, instead of minus, here is a plus. But then there is a quartic term, which is with minus phi to the 4. So there was just so what I have done, I take this amplitude where it is. So here is the amplitude. You see here amplitudes A1, A2 is equal to this. Amazing thing that if you make the substitution, momentum you divide by GH and x mu you multiply by square root of GH in here. So you see here is the momenta K, K2, and there is a coordinates x. If you do this exchange of the coordinates, the dependence on the field is factorizing. So that was I don't know, this thing they did not. I discussed with Holger and with Jan. They did, for some reason they did not have seen this. So you see this this integral, which depends on the field and coordinates and momentum. If you do this substitution, which I find before, so you see again the dependence on the field factorizes, and the action does not depend on anymore on fields. So therefore, here also you have 1 over g squared in the power of g squared, which is give you the h squared logarithm h. So they call it a hidden Higgs mechanism. And they was trying to find some field configurations which are generated by using this some ansatz for phi k2 field, and they find this magnetic tubes and spaghetti, you know, all these things. It's come from the solution for this amplitude of negative modes, right? But the trick is that you just can integrate exactly over them. Yes, so, and that's recover the same expression.